Angular velocity and linear velocity can easily be converted between because a linear velocity is equal to the radius of rotation times the angular velocity. And likewise, the angular velocity is equal to the velocity divided by the radius of rotation. So a problem which this is useful in on the AP test is problem 31. This problem has a mass, a particle of mass m moves counterclockwise around a horizontal circle with radius r as shown above. The angular speed of the particle is given as a function of time t by the angular velocity is equal to bt, where b is a positive constant and t is greater than or equal to 0. So we can start by drawing out what's happening. We have a circle which a particle is moving in, and the particle is shown to be at the very top of the circle in the diagram. So we'll draw it like this, just a little bit bigger. So this is pretty much our diagram of our moving particle here. And our question that we're looking at is asking which of the following best describes the acceleration vector for the particle at the moment shown in the diagram. So we want to see which way this particle is accelerating. So we want to convert the angular velocity into just a vector of velocity and take the acceleration from there to see which direction it's in. So here we can do this by saying that v is equal to our rotational velocity. And in this case, our rotational velocity is equal to bt because that's given. So our velocity is equal to our bt. So that's the magnitude of our velocity, but we want to find the separate components of this vector. And we can do this by including another component of this particle's movement, which is the angle theta from where it is in the circle. So I'll draw this out as a visual. So the angle theta between where the particle is. So right now it looks like it's just 90 degrees. So we can divide up its motion into separate components by saying that the velocity is equal to the x component will be r b t times sine theta because that's the component which is moving in the x direction, the sine of theta. And then our y component of our velocity will be r bt times the cosine of theta. Just like this. And so now we want to find the acceleration. And as we know, the acceleration is the derivative of the velocity in terms of t. So we're going to take the derivative of each component of this vector. So vector of a is going to be equal to, well, we know that these are all pretty much constants except for t, so we can remove t from the equation. R b cosine theta? Well, I mean, theta is dependent on t, but we can take the rest of t out of this because we are integrating or we're taking the derivative, not integrating. So what we get is RB cosine theta in for our x component and negative RB sine theta for our y component. And at the time we're looking at, theta is equal to 90 degrees. So we want to evaluate this for 90 degrees. So we know that sine of 90 is going to be equal to 0. Or we know that, that cosine theta, not sine, is equal to 0. So our x component cancels out completely, and there's no component of this vector in the x direction. So a equals 0, comma. And then in the sine direction, sine of 90 degrees is just 1, so we have negative RB. And so if we visualize this vector, it's only pointing in one direction, in the downwards direction, because all we have is a y component, which is negative, and that negative sign indicates that it's pointing in a downward direction. So from there we know that the acceleration is directed towards the bottom of the page only, which is answer B of question 31 on the AP exam.